All right, good. We're all set. So thank you, Pablo, for accepting the invitation. So today we have Pablo Arrighi from Université Paris-Saclay. And what's actually QUACS? What's the
QUACS is quantum computing structures, and that's the name of our team.
All right. And you will talk about quantum network theory. Pablo, whenever you're ready.
Okay. Thanks a lot for the invitation. So I'll try to stick to the 30 minutes. So maybe I'll cram things a bit, but then there'll be plenty of time for discussion. So I'm indeed in this QUACS team of the LMF, Laboratoire de Méthode Formelle, of the Université de Paris-Saclay. That's also where Amelia is at the moment. She was a PhD of mine in Marseille right before that. And this is joint work with Matthew Wilson also, who is a PhD at the University of Oxford. So this quantum networks theory stuff is mainly about two things, about a new tensor product, a generalized tensor product, and the associated traceouts, and also about extending quantum theory over discrete systems to graphs and to unitary operators over a Hilbert space that is spanned by graphs. Those are the two main things I want to talk about. And I'll start with the tensors and then move on to the latter. And that is where I think I can highlight possible intersections with the quantum gravity community, since this KINS consortium is about that, about intersections between quantum information and quantum gravity. I believe that there are here some mathematical tools that can help address questions such as unitarity and causality in the context of quantum gravity. Okay. So first of all, let me tell you about, just the mathematical framework in which I want to discuss things, just so that it's not just pretty pictures and we know what we're talking about. So I'm going to make some little drawings like that. Those are called systems. What is a system? A system is basically a node, a vertex that has some internal state. For instance, it could be white, it could be black. This internal state is basically in some finite set, sigma. And this node also has a name, like you would say, this is the system Alice, this is the system Bob. Okay, so it has a name. All right. So once you have this definition of a system, you can define what graphs are. So graphs, they are just sets of systems. Each of the systems making the graph, they need to have a name that distinguishes them. So the names are unique. And why do I call this a graph when there is no edges? There are no edges, but I will introduce edges later, right? So just bear with me on that. So for now, graphs are just sets of colored vertices. So there is curly G, which is the set of every possible graph. It's a countable set. And so you can consider formal quantum superpositions of graphs. That is, you can consider the Hilbert space, whose orthonormal basis is basically given by the set of graphs. Okay, so that is the states, the state vectors, the pure states of the quantum theory I'm talking about are basically norm one vectors of the Hilbert space that is generated by the graphs. Okay, so now let me talk about tensors, and let me get back to the good old tensor product and remind us of the fact that here are three systems, U, V, and W. And I could very well write this like that. That is, I could put U on the left and separate it from the other two with a tensor product. But I could also have written UV separated from W. And so these three things are equal. But you see that this symbol here is not quite the same as this symbol here because it does a different split. Okay. So perhaps I could, for a start, want to be a bit pedantic, a bit, and I would like to say, well, those aren't the same symbol. So maybe I need to specify what I mean by a tensor product. For instance, I could distinguish the two symbols and say, this is a tensor product that takes the U apart, and this is a tensor product that takes UV apart on the left. Okay, just more notation to be more precise, if you like. But then once you start doing that, you may wonder, okay, but how far can I go with that? I mean, what are all these the chi's parameterizations of a tensor that I could, that I'm allowed to play with? For instance, am I allowed to split a graph not according to the names of the systems, not according to, oh, here is Alice, here is Bob and Charlie, but rather according to the color of the nodes. Like, okay, here are the qubits that are 0, and here are the qubits that are 1, for instance. And this is what this tensor here, parameterized by mu, does. It takes the marked guys and puts them on the right. And it's interesting to consider that because you will suddenly realize that the very notion of who goes left and who goes right becomes quantum by itself. For instance, here I have a superposition of two possible configurations of two possible graphs. And as I split it according to this tensor, well, there is a branch in which there are two systems on the left and one on the right, and another where there is one system on the left and two on the right. So you see that the very notion of who is left and who is right becomes quantized, and that is the kind of thing you will want for quantum superpositions of geometry. But I will come to that. Okay. So you see that I'm starting to play with the idea that I could parameterize my tensor product with strange things like mu and what was it, Ku, KuV. So what is the set of every possible strange thing you could put there to parameterize your tensor product? Well, we've studied that carefully, and the mathematics eventually told us, if you like, the necessity of the math brought us to consider this condition here. So, okay, so let me just be a bit clearer. So these restrictions, chi, they are functions from graphs to graphs that take a big graph and it keeps just a piece of the graph. For instance, it takes a graph of two nodes and it keeps just a piece of the graph, okay? And there are restrictions if they obey this condition here, which is, well, it basically says that if G restricted is G chi and you take some guy in between, some H, well, then the restriction of H has to be equal to the restriction of G, okay? Well, some examples are the ones that I've provided so far, like the Chi-U, the guy that isolates system U, is such a restriction. The mu, the guy that keeps the unmarked nodes, this is also a restriction. In general, many things are restrictions. Basically, these restrictions are sort of, they have, you know, if you restrict twice, it's the same as restricting once. So in that sense, they are oblique projections. And if you have two restrictions, well, the union of two restrictions is also a restriction. By the way, I'm denoting by chi bar the rest of the graph, right? So if I've got chi a restriction, and so you have your G, gchi, the restricted graph. You complement that, and you'll get to the gchi bar. Okay. And also, quite interestingly, later for more quantum gravitational ideas, if you have a graph, this time with some connectivity, and you single out a node, for instance, a node V, if you look at who are the R neighbors, the radius R neighbors of V, well, that defines also a restriction. Okay. So a restriction is just a way of singling out a part of a graph, right? And once you have a way of singling out a part of a graph, you can define a tensor product. Here is how. So this generalized tensor product is a bilinear operator from, well, what does it take? It takes two graphs and it gives you back a graph. Because it takes two graphs, it tries to do the tensor product of them, and that will give you back another graph. So you see, that's one difference already with the usual tensor product, is that it's an operation now, it's a binary operator over the Hilbert space. It's not something that takes a Hilbert space A, a Hilbert space B, and constructs AB, right? It's actually taking the large Hilbert space. Okay. So how does it work? Well, you give me a graph L, you give me a graph R. I look to see if there exists a graph G, which is such that L is the chi restriction of G, and R is what's left over. And if that is the case, G is the answer. If not, I give you back the null vector. That's for the basic case, right? That is for two graphs. Right? In general, you could have superpositions, but because this is defined to be bilinear, this defines the behavior of the tensor product over the whole space here. Let me give you some simple examples to start with. Well, this chi u is the guy that keeps the U system on the left. So if I give it that graph and that graph, that's okay because that graph is indeed the chi restriction, the chi u restriction of some graph, and this is indeed what's left over, right? So this is going to give you back this. Whereas in this case, you see that there is a little problem. You're feeding the u on the right-hand side, but chi u would keep that u, it would keep it to go to the right-hand side. So that should give you back the null vector. So similarly, here there is also something that is inconsistent. Chi u, it would never leave behind a u on the right. Okay. So funnily, you can define these very generalized tensors, but you can also define their corresponding partial traces, trace outs. Okay. And here is how this works. Well, again, you say the trace, this is the trace out, that the thing that keeps chi, right? So you need to apply it to trace class operators over the Hilbert space, that's normal. And you can define it over the basis states, the ket bras. If you have done it on the ket bras, you've done it for everyone by linearity. Okay, so how does it work? You say, well, from this ket bra, what I want to keep is the part that is on chi. So I'll just keep g chi, h chi. However, I need to trace the rest. So I need to check that on the complement of chi, these two graphs are equal. Okay, and so just to give you some examples, this thing here, so I want to restrict on u, so I'm going to keep this guy and this guy, but I'm going to check that this guy and this guy are equal, and they are, And so this is what I return. Here, V and V here, they're not equal. They don't have the same color. So this is going to give you the null matrix. And here, again, the complement of U isn't the same. So this is going to give you back the null matrix. Okay. So this perhaps sounds like a bold step. I mean, quantum mechanics has been around for a long time, and the tensor product used in that formalism for, I don't know how many years, maybe 100. And so those definitions of new tensor product or new trace, yeah, they may sound like a bold move. So you need to be careful, you need to be cautious, you need to check that this is sound, right? So one way of making sure that this is sound is to make sure that, well, for instance, you have some good properties, like you're going to, your trace out is indeed going to take a density matrix into a density matrix. This is the case. We can prove that this operation is a trace preserving, completely positive map. So it's a perfectly sound quantum operation. It also has some properties that you would expect, like if zeta is a restriction that is included in chi, well, you'd expect that if you do the trace out to just keep chi and then the trace out to just keep zeta, it's the same as just keeping zeta, and that's also the case, right? Still, maybe I haven't quite finished to convince you, because you know, there are so many properties around the tensor product and the trace out that, you know, okay, fine, this is a quantum operation, but there's so many other things to check. So at that point, I want to just take a little step back and say, okay, but first of all, why do we use the tensor product, the good old tensor product? What do we use it for, generally speaking, in quantum theory? And it seems to me that we use it to separate systems in order to have good notions of locality. Like, I want to define an operation that is local on system A, for instance. And we also use it to be able to formulate conditions like signaling, like if Alice does something and then there is an evolution, will the something that Alice did have an impact on Bob's system at time t+1? This is what I would call causality or signaling. I mean, those are the main reasons why we use these symbols to begin with in quantum theory, right? We can also use them to describe entanglement and so on, but it's always this question of separating systems. Okay, so here are some results, some mathematical results. First of all, about locality. Okay. So, wait, what is locality? Locality is, well, imagine you have a big bunch of systems and you say, I'm local on some subsystems. Which subsystems? Well, the subsystems that are described by chi. Okay, so let's say that some operator A is local on chi. Okay, what do you mean by that? Well, what you mean by that is that it really doesn't touch anything but chi, right? It does something at chi, it transforms that into some other graph or blah, blah, or superposition of it, but here it doesn't do anything, okay? So there are different ways to formulate that, mathematically speaking, in quantum theory. You could, for instance, say that your amplitude of transition between G and H through A is given by this formula. That is, the two must be equal outside, and the amplitude actually just depends on these two here. Or you could say that A is actually a tensor product of something trivial outside chi and something non-trivial inside chi. Or you could say, well, if A is actually an observable, a local observable, that should only depend on the reduced density matrix on chi, the result, the probability. Okay. It turns out that all of these statements, they are equivalent for the tensor product and the reduced density matrix usually, and they still are with those generalized tensors and reduced density matrices, right? So you have a sound notion of locality, and you can really say, okay, I'm gonna modify this node into a superposition of nodes, say, and when you speak about this node, this system, you can parameterize that on any restriction. Okay. You also have a sound notion of causality. So causality, again, is this idea that at t+1, okay, so here, for instance, you have some particles moving. Well, at t+1, the particles that are here, that only depends on where the particles were at t on a small neighborhood around V. Right? That's what we mean by causality. It's this idea that some region defined by some restriction zeta, its state at time t+1 only depends on some neighboring region at time t, maybe defined by some restriction chi. So a unitary operator is chi zeta local, if that is the case, and there are mathematical ways of writing that. One way is to say precisely what I just said here in terms of trace outs, in terms of reduced density matrices. Here is the more algebraic quantum field theoretical way of describing locality. It's about saying that some observable here at time t+1 is equivalent to an observable on a larger neighborhood at time t. And a more hands-on way of talking about causality is to try and describe U as a circuit of plenty of little local gates that happen in parallel and that decompose U. All of these things are, again, equivalent. They were for the old tensors and traces, and they are still for these generalizations. Okay. So, yeah, so we have to conclude that somehow the good old mathematical results that we are used to work with when we deal with tensors and traces, they carry through, they generalize. Okay. So why would you need to generalize them anyway? Okay. Well, first of all, it's kind of nice to have a general way of splitting a large system into subsystems. Okay, it's actually something that you see happening in many papers. That there's this virtual subsystem idea, and you get that. In various contexts, there is this idea, for instance, that entanglement is relative to a certain split. So here is an example. If I separate according to U and V, this is a product state. But if I separate according to black or white, then this is an entangled state. Okay, fine. Another context in which this sounds an interesting thing to do is the whole study of quantum reference frames. So here are a superposition of two graphs, and you see that the white node is in a superposition of being at 0 or at 1. And yet, maybe I would like to take the point of view of the white node and try and figure out what the white node sees, okay? And if I actually take this mu tensor, the one that takes out the unmarked node, this is more or less what I'm doing. I'm isolating the white node from the rest. And I realized that whereas the black node seemed to be in a well-defined place, now it kind of seems to be itself in a superposition of places. However, there's a quite a little difference here between our formalism and that of quantum reference frames, which is that we keep the name of the nodes here. And we have good reasons to keep them because we have an argument in this paper with Marios and Amelia about the fact that that forgetting about names may trigger some no signaling effects. Anyway, another situation in which this can apply is the following. So we are very aware in this KISS community that with quantum theory, you can superpose data, but perhaps you can also superpose programs or circuits, and you can superpose the order of applications of some gates. But in this circuit, I realized that this wire can talk to this wire, and here this wire can talk to this wire. So if I kind of flatten that, if I flatten that into interactions graph saying who is next to whom, like who can signal to whom, I get that this superposition of circuits is actually a superposition of graphs, of topologies. This idea of superposing geometries is, of course, the daily bread of quantum gravity, and particularly in the loop quantum gravity approaches. And so you may perhaps compare this with superpositions of spin networks. Okay. So what I'm saying is there are various motivations to consider quantum superpositions of graphs, but in those superpositions of graphs, it becomes kind of difficult to talk about locality, because when you are in a superposition of being next to a guy or far away from the guy, what does it mean to be local? What does it mean to be causal? Okay, that becomes quite a slippery business. And in particular, the good old notions of, well, let me take the tensor product between Alice and Bob and figure out signaling there, they sort of no longer really work. And this is why you're going to need some more robust notions of splitting out systems. Okay, so I think I will probably be 5 minutes too long. I apologize for that, but I'm not so far away from the end of the talk. So before I can really speak about these quantum superpositions of graphs, I need to talk about a few technical difficulties here. So I hope you bear with me on these little technical aspects. So let's say that I have a node, and that node is called U, and that this graph evolves unitarily into a graph that now has two nodes. Well, I have a little difficulty here, which is how on earth am I going to call that second node? Will I call it V or W? That kind of sounds a bit non-deterministic or non-local to suddenly pick up a name, W, YW. And in particular, this could be, it could be, if the two choices are possible, then it's non-unitary, because I will kind of forget my choice as I go back with a U dagger. So the way to solve this is through a little name algebra. You could say, well, U is going to infant two names, u.l and u.r. Okay, and now if I do a u dagger, well, I'm going to have to merge these two names into u.l merge with u.r. And now you see that I need this merger to be equal to u. So I need this equality. And for similar reasons, you also need that you also need to have these two equalities. Okay, so you need to have a little structure, a little algebraic structure on names. Just like 1 + 1 is equal to 2, you need to have that u.l v u.r is equal to u. Okay. Now, once you have this structure on name, you can solve another little technical difficulty, which is, okay, hey, here are two graphs, two possible graphs, disconnected, connected. Let me split them according to this mu tensor, like I'm keeping the unmarked on the left. Okay, but now, okay, so I do the tensor of u and v. What should I get? Should I get this graph or the connected graph? So the question I'm asking is like, when you split a graph into two, where do you put the connectivity between the two parts of the graph? Those are annoying technical questions, but you need to solve them at the end of the day if you want to be able to talk about locality and causality over graphs. That's you just can't skip them. And so now that we have this little structure over names, we can actually make use of that to encode the connectivity. So here we proposed to adopt a convention, which is that because there is you see, if I want to encode that this white node is connected to this black node, well, I will do that through the names. I will call this node maybe yv minus zeta, and the minus zeta is telling me that I'm connected with the zeta. And that way, this situation is resolved, because when I tensor this guy with this guy, I induce that there is an edge. All right, so that was a bit technical, but the point is that once you've done this naming conventions, you can encode graphs with connectivity. And now everything that I told you about earlier on carries through. All of these theorems about locality, causality, they work out. So you're suddenly able to speak about some local operation over a graph that, for instance, it sees a black node. Well, it's going to split it into two nodes, which is a model that actually was proposed by David Meyer, who is in the consortium together with Haslesher. So you can actually really talk about the causality of operations that actually change the graph. And you can even talk about the locality of operations that change the graph in a superposition of not changing the graph, for instance. So now you're really able to talk about this idea of, here is a graph, I'm going to act locally, and that's going to produce a superposition of graphs. And I know what I mean by local. This is very formal. It relies on all of this theorem. And again, you can talk about causality. And so you can really talk about these quantum superpositions that evolve into quantum superpositions. And you're able to say, well, the surroundings of this node is actually only influenced by its surroundings at the previous time steps. So you're really able to talk about causality in, if you like, spin networks evolutions, if they are formulated like that, synchronously, or any sort of fully quantum network evolution. And I want to draw your attention here on the fact that amongst these equivalents, there is one which says that any unitary causal evolution must decompose into local gates. So that is telling a story here, which is that these big unitaries over quantum superpositions of graphs, they actually decompose into local unitaries that rewrite the graph. Okay, so formulated perhaps in terms of quantum gravity terms, this would be suggesting that if you don't want to break unitarity in your quantum gravity, then you should be careful that your vertex amplitudes, like the local mechanisms you describe to evolve your speed network, that those be themselves unitary. Okay. So I thank you for your patience. I'm a bit over time, but here is my last slide. So let me just wrap up. We started from the idea that a tensor product perhaps could enjoy a more precise notation because usually we have the same symbol for many things. And then we thought, but how far can I go with this? And how far can I go at parametrizing tensor products? And this gave us the notion of restriction. We then realized that locality, causality, whether phrased in the Schrödinger picture and the operational picture, in the Heisenberg picture, all of these notions, they carry through, and all of their logical interrelations, they carry through. And the applications were, well, it's this idea that maybe the tensor is a bit too rigid in order to define subsystems. That's a recurring idea in quantum mechanics. This general tensor product is also a way of taking the point of view of a superposed observer. And well, finally, it lets you talk about the neighbor of a node, even in very wide context where you have quantum superpositions of graphs. And so it lets you talk about the neighbors, it lets you talk about local operations over neighborhoods, it lets you talk about causality. And so it seems that it is the appropriate mathematical language to deal with questions of unitarity, locality, causality, in particular in quantum gravity. So I'm done.
Thank you. Thank you, Pablo. Okay, are there questions? You can raise your hand or yes, just unmute. Okay, I think Laurent was first. Go, Laurent, please.
Yes, thank you for your nice presentation. It's very interesting. I had a question about these results of unitarity, locality. Could you elaborate on that? So are you saying, because I can imagine that I have a network and then I have a unitary evolution which is completely non-local, but you seem to be saying that necessarily it has to be decomposable in some way.
Yes, exactly.
And you had this notion of chi locality, which I'm not sure what it meant, but
yeah. So let me try and.
I missed the first slides. Maybe
I should draw a picture. Okay. So I think I can write here. Okay. So what you have here is some local rewriting of the graph, right? I've got a graph and I just rewrite what's inside the disk. Maybe I rewrite it into a superpositions of disks, but okay, so this is something local, right? And what I'm saying is that if you have an operator over entire superpositions of graphs to entire superpositions of graphs, and such that if you take some node here and you look at a very small neighborhood, maybe just neighborhood 1. Okay, tac. This neighborhood is actually determined by the neighborhood at the previous time of V. Okay, so this is what I mean by causality.
Mm-hmm.
Then, so this premise implies that U is actually a product of K's.
Mm-hmm.
Of K's applied everywhere. Like you need to take U inside, every possible name, if you like.
Mm-hmm.
And actually, you need another little product here of U. Okay. Okay, so I'm saying basically, so if information doesn't propagate too fast, you have a big evolution from superpositions of graph to superposition of graph. If information doesn't propagate too fast in the sense of graphs, then U is decomposable indeed into little K's, and those K's, they need to be unitary and local.
Okay, makes sense. So yeah, unitarity and causality. No, it's very clear. And that fits the kind of the naive picture that people in spin form or in loop gravity use when they think about time evolution. Can I have another question? I mean, I have another question. Maybe I go back into the queue. Okay, go. The next person can.
Yeah, just so I think it fits the intuition, but on the other hand, from what I see, you in quantum gravity, you tend to describe your evolution through a Feynman path integral formalism, where unitarity is not so clear. I mean, it's not so clear that you have it, and at the end of the day, you end up parametrizing that. I mean, the thing that describes the Feynman path integral at the end of the day is the vertex amplitude, and the vertex amplitude. I'm not sure whether it's possible to say something about their unitarity.
Okay, so maybe that's the second question. This evolution is unitary. The nodes cannot change, or they can change the number of nodes in your.
I can change the number of nodes. Yes.
Okay. And just a question, maybe when you measure the speed, there's two naive measures. You can count the number of. Let's think about your disk. It's a sphere, and then there's the inside and the outside. So you can count the growth of the number of nodes inside, but you can also count the number of edge that cuts the sphere, right? So which one? How do you see what I'm saying? And you can count the dimension of the Hilbert space of the edge that cuts your sphere. So which one do you use to kind of measure the causality?
I measure. So I'm not talking about dimension here, like emergent dimension or anything. I don't have anything to say about that. Here, when I talk about distances, I mean graph distance, like up. You've done one step here, and you've done two steps here. Okay. So,
but because in quantum gravity, the distance is also proportional to the the dimension of the Hilbert space that the link carry. So you don't have that possibility in your description.
So I guess I think you could put labels on the edges. And then say, well, if there is a label 3, then that represents a distance 3. Is that?
Maybe I could comment on this. It's very interesting. I mean, I'm happy you're having this discussion. So I think, how to say, in a sense, not in a sense. I mean, what Pablo is talking about now is essentially topological. He's just talking about distances of the graph. I think. Something that confused me a lot discussing with Pablo to understand what's going on is that, defining the graph and naming the nodes which defines the graph is a completely different procedure for him than coloring the graph.
Mm-hmm.
So that is something that has to come on top now.
Mm-hmm.
So whether this notion of causality or locality is going to coincide with what you would expect if you color with spins and the rest, and you interpret those as eigenvalues of operators, I think that is a different question than what Pablo is saying, which is, it would be nice if it's like that, but I don't think it follows from just what he says. I mean, I don't want to put words in the mouth of Pablo, but this is my understanding.
I think there is a bit of work to be done to adapt. It's not, doesn't directly follow, but doesn't seem incompatible either.
Okay, yeah, so maybe the question, because my confusion was that when you start to talk about superposition, you have to tell me what is the Hilbert space of superposition you can take. So that's why, for me, isn't there this hidden information somewhere about the size of the edge, like the, you know, how many, what is the size of the Hilbert space you, because yeah, Mario says purely topological. So you're always assuming that secretly it's a qubit. I guess that's what I have in mind.
Well, so to construct a Hilbert space, you can do that as soon as you have, as soon as you take superpositions over a countable set, right? So here I'm taking, I'm imagining that the internal states, they're in some set sigma that usually take finite. Maybe it can be taken countable, I don't know. But then I take sets, I mean, I define my graphs to be finite, although unbounded, but finite. So there is a finite number, there is a countable number of such graphs. So then I can define a Hilbert space of formal superpositions of those graphs. So if you like, I don't know if that answers your question, but mathematically speaking, it's just.
I mean, I understand. I mean, the qubit is the edge is on or off. That's all. That's the qubit I was talking about. Because what matters in quantum gravity is the connecting edge. So for you, that's where Mario says it's topological. Then on top of that, maybe we can put, you know, the edge could be on and off, but when it's on, it has an associated Hilbert space that represents what we call the quantum geometry. But that's okay. You know, geometry comes after topology. I agree. I understand that. Thank you.
Yes, that's how I understand it too. I will move to Amin and Halem. We could come back, Laurent. I think it was very clarifying. That's why I also let it go. Continue. I think Amin was the next question.
Okay, yeah. Thanks a lot, Pablo, for this very nice talk. It's very, very fascinating. I have a question about this difficulty 2 you mentioned. So as I understand, the edges, you encode them with the labels of the nodes, right? So
yeah, I call those names rather, but
or names, yes. The names, they define the edges, but I was wondering why not always keep an edge? So having an extra relation that defines the edges, and then whenever you do this, you always keep an edge if the edge is present, and the partner node is also present. Instead of moving it to the names, right? To have really a set of vertices and a set of edges, and then working on that.
So, right. So whatever formalism you choose, you need to choose a formalism where the information about whether there is an edge or not sort of, you know, if you decide to suddenly split, like split here, it needs to survive, and it needs to survive on both sides. It needs to be there, and it needs to be there.
Yes.
If you don't do that, you run into technical difficulties that I have experienced for
okay.
So then, apart from that recommendation, I would say that there are probably other conventions that can be taken.
Okay.
Yeah.
I was just thinking naively to have, in addition to the nodes, so the graph is now defined as a set of nodes with internal states and names. but also to add a relation which describes the edges. So also for directed edges, for instance, or whatever. And then the cut would then just be, okay, if there's an edge, well, and the remaining node is still present after I do the operation, then I keep it. Or then I could also do operations on edges. I could just remove edges. Things like this.
Yeah, I think it could work. It's just, yeah. You have to look at the technical details.
Okay. And then with directed edges, you would deal now in the same way, as I understand.
So those are directed if you want.
Yes, I see.
You could say that this is directed towards there.
Yeah.
And then you could define directed or not directed neighborhoods. In a way, the stuff that I've presented you is very, very general. I mean, the thing is, your notion of a neighborhood is really left to the user, to the mathematical user. The mathematical user has to check that that he's going to split the world according to a criterion chi that verifies this condition.
Mm-hmm.
And if that's the case, then you can go on. You can proceed with your math. All the theorems will work out.
Okay. Okay. Nice. Good. Thanks. Yeah.
Thank you. Hal.
Thank you, Pablo. This is a very interesting talk. I'm deeply interested in this question of the identification of subsystems. And I'm worried that I didn't understand your very first step, and I'd like to catch it carefully. So you say that you're going to talk about graphs and that graphs are collections of names. I'm stuck in the old way of thinking, and I think, okay, I've got a Hilbert space, it's my total Hilbert space, and I can break it up into tensor products. And that's, of course, you can't start there because you want to generalize the notion of a tensor product. So I'm a bit lost on how you're identifying your subsystems. What picks out U and what picks out V?
Yes. So you're right. So you shouldn't consider that the space has been constructed by tensoring qubits. That's not the way you should think about it. You should just think of the resulting Hilbert space, if you like. You should imagine, here are 3 qubits in state white, black, white. Here's just one. Here is, okay. And that's already a Hilbert space per se, right? They coexist in this kind of, maybe we could say a kind of Fock space, but it's more like, it looks more like a occupation number representation of a Fock space, if you like. Okay.
Sorry, because I was not a big. Black and white requires the being part of one subsystem or not? Is that?
So, black and white is the internal state of a subsystem, I guess.
Okay. Yeah. I guess, Al, maybe that's your question, but I'm confused about it. Suppose, how do you decide that this bit is inside your subsystem or outside your subsystem?
Okay.
What's the coloring?
Yeah. So that's what I was going to say. So what I mean is, so first of all, you need this very large Hilbert space, which has got everyone inside. It's got the 3 qubit state, it's got the 4 qubit state, it's got everyone. Okay. And then you decide how you're going to split. And the way you decide is by actually deciding for yourself of a certain function, chi, which takes a configuration and gives you back a smaller configuration. For instance, something that takes a large configuration like that and gives you back a smaller configuration. According to what criterion? Well, depends on your function. Your function tells you the criterion. You're the one who decides how you're going to split. Okay, it's like in math when you have a discriminating function that defines a subset of a set, right? Chi is a discriminating function, if you like.
But it's very classical. So why can't it be that chi is a superposition? Like maybe you messed up your notion of locality. You describe it in the wrong basis, or is that? So for you, locality is always kind of classical, attached to where the nodes are. Or well, I mean, that's a definition. I agree, but
it's yeah, you could say it's classical.
So you start all your edges are labeled.
Defined with respect to a basis. The Hilbert space is taken as spanned by the graphs, and in that sense, we don't overgeneralize the tensor. I mean, the tensor, the good old tensor, it's you have to be in a basis, and then you can say, oh, here is how I split.
Right, but you so you do have superpositions of arbitrary graphs in that Hilbert space.
Yeah, we have a superposition of arbitrary graphs, but
what don't even have to be the same graph. And if they have a node named U, and you say I'll choose the one link neighborhood of the node named U in a superposition of graphs that have a node named U, you're going to get a superposition of stuff. Right? It does. I'm just saying it does extend to.
Yeah. So he has a locality of the labels, but you can think of locality which restrict the labels from one label set to a sub-label set. But you can have a locality of the Hilbert space. You can say, well, I want to map this big Hilbert space into a sub-Hilbert space. That would be a more general. A label is just one way to have a sub-Hilbert space map. There's classical locality versus quantum locality. It's okay. You're having a notion of classical locality based on the classical labels of the graph.
I agree. I mean, I agree. It's defined on the basis, at least. It's defined with respect to the basis.
Yeah. You have to assume there's a universal preferred unique basis, right? Like space-time, or I mean, that plays the role of your topological space-time.
Yeah, that's right.
Laurent and I are on the same page here. It makes sense for a relativist to worry about this, because you could label points of space-time with labels, but we know that those labels, they get all mixed up when you do a diffeomorphism or when you make some sort of covariant change, right? And so that it's worrying. I worry about this label from the outset.
Right. That's what. Okay. I'm sorry to Pablo. I can shut up if you want. This is exactly what I said to Pablo too when we started discussing. But we do put these labels, right? We put coordinates to have the manifold, if you want. We coordinate this manifold, and then we demand the Morpheus invariance. And I don't know how much it was stressed here, but the point is that the observables and what you're going to call evolutions and observables, you want them to be renaming invariant and the renaming of the nodes. So you use this as handles to say stuff, but you don't treat them as anything that has any physical significance. This UVW things is like arbitrary coordinates on your graph. Then you can change the names. But there is a rule on how you can do that to be consistent.
Mm-hmm. Yeah, right. And I guess maybe we're trying to be too general with HAL and the thing, but it's really about diffeomorphism invariance. So that it's a struggle that quantum gravity has had since the beginning, is that if you pick a graph and you name ESA your nodes, which is what you're doing, and then you say, oh, the only thing I can do as diffeomorphism invariance is just changing the label of the nodes. Okay, then that's not diffeomorphism invariance, because we have example in the phi theory where a diffeomorphism invariance is a unitary transformation in your Hilbert space. And of course, relabeling the nodes is a very particular, unitary transformation that doesn't allow superposition, of your basis. So it's like you have a notion of absolute locality and you cannot get beyond it, right? But that's not a criticism. We are there, and maybe, it's just awareness that we are restricted to that concept, and that's
yeah. No, but that's something we've been thinking about quite a lot. And in fact, so this paper here is the one Marius is talking about. Mm-hmm. And so we discuss these things a lot.
Okay. Yeah.
If you have a strong argument why diffeomorphism invariance in quantum gravity should go beyond that, then I'm really eager to know about it.
I can give you a one-line argument. Yes,
okay.
Which is if you think, okay, maybe, but I don't want to. If you think that quantum gravity is something that has to be a preferred length scale and the possibility to preserve Lorentz invariance, which is a subset of diffeomorphism, then the only way you can have discreteness and preserve Lorentz invariance is by allowing Lorentz invariance to change the basis. Like it's the reason behind the quantum mechanics, right? If you want to preserve discreteness and symmetry, there's a tension to it that only quantum mechanics can resolve. So that would be the simplest argument I could give you.
Because I can give you what my liner would be, my one liner. But okay, I'm entering a debate that it is maybe a bit philosophical. I don't know, but so let me just make a little drawing. So let's say that I have.
Just a question to Marius. That discussion recorded? It feels we're like outside of the recording.
We're still recording. You want me to stop that discussion?
Yeah, I mean, yeah, I think we're beyond. Yeah.
Okay. Is there any other questions? I think that's a good point.
Maybe we can come back to that then.
If not, let's thank the speaker and yeah.